Irrationality of the square root of 2. Here is the task for this video. Use the proof by contradiction to prove that square root of 2 is irrational. So this is the question here that we want to address. Is square root of 2 irrational? Before we answer this, we have to understand the meaning of words, and therefore let us start with trying to think about what a rational number is. So any number in the form p over q, where p is an integer and q is also an integer, while q is different from 0, is understood as a rational number. For example, 2/3, minus 5 over 8, number 4 itself, because number 4 can be written as 4 over 1, and so on. So all these are rational numbers. And now what we know about rational numbers is the fact that each rational number has a decimal expansion which either terminates or recurs. So for example, number 4 here has the decimal expansion 4.0000, etc., or we just write it's 4. And this means that the decimal expansion of this number ends at this digit here and doesn't continue any further. For example, number 0.24. This is the example of the situation in which the decimal expansion terminates. And the reason why this is a rational number is that this can be understood as 24 hundredths. Okay? And this is a fraction actually, and it is in the form of p over q. This can be also written in the simplest fractional form. We can cancel common factors out, but I'm not going to do this here. This another number here, 0.123, 123, 123, and so on, is an example of a number, a rational number, which has a recurring decimal expansion. You may remember from previous years that if I denote its value by x and write it like this, 123, 123, and so on, and if I multiply this by 1,000, so multiply by 1,000, what I get here is 1000x equals, and then it's 123.123, 0.123, 0.123, and so on. Sorry, just wrong digit here. And it continues forever. And if we subtract these, and we subtract 1000x minus x, it would be 999x, 999x, equals, and if we subtract these, the infinite decimal expansion cancels out, or it just disappears, and what I get is 123, and hence x is a fraction 123 divided by 999. So this was our proof in previous years to show that numbers with recurring decimal expansion are actually fractions or rational numbers. There are, however, some numbers which do not have a recurring nor do they have a terminating expansion, and these numbers are not rational then. We call them irrational numbers. So numbers which cannot be expressed in the form of a fraction with p and q as integers. Now, decimal expansion of square root of 2. Well, if you use your calculator and type in the square root of 2, this is what you get. It's 1.414, etc., etc., etc. So if you look at this, it doesn't seem to be terminating anywhere, and also there is no any recurring pattern there. Well, it doesn't mean that it's really not there. It just looks like there is no such pattern. Maybe the first million digits, when they end, they will start again from the beginning, recurring, but we cannot say that by using our ordinary calculator. We would need special calculators or special software to prove that, but even then we would not be sure that there is no recurrence. If we saw that there is no recurrence after 1 million digits, what can be for us something that would persuade us that there is no recurrence after 1 trillion or one however many digits. So this is not the way to go. So we cannot prove that square root of 2 is irrational by writing out its decimal expansion. But luckily there is a proof that we can use to see that the square root of 2 is really irrational, and it doesn't have to do with writing out its expansion. It's something that is very nice, and I want to show it to you. And it is a method that we are going to use. It's interesting here. It's called proof by contradiction. This is used very often in mathematics and also in ordinary life, that you can run across this proof, but maybe it's hidden. Well, okay, so what is it? What's this proof? We suppose that the opposite is true of what we want to show is true, and follow a series of logical steps until we arrive at a contradiction. Contradiction in Slovak it's spor, a ten dôkaz sa volá dôkaz sporom. So we suppose the opposite of what we want to prove and try to arrive at a contradiction. And this means the contradiction confirms that our original supposition must be false, because only false suppositions can lead to contradictions. Okay, so let us make this proof now. I will show you how to prove this fact that the square root of 2 is irrational. So we want to prove that the square root of 2 is a rational number, and when using the proof by contradiction, let us suppose the opposite of what we want to prove. Let us suppose that the square root of 2 is a rational number, and let us try to use logical steps that would lead us to some contradiction here. So let us suppose that the square root of 2 is p over q, where p and q are both integers. P and q are integers, positive integers, because the square root of 2 is positive. And let us suppose that p and q are in their lowest terms. It means that this is the simplest rational form of this fraction, that you cannot cancel anything out in with these two numbers. What I mean is this: p and q are already in their simplest form. It's not like 8 over, say, 6, because here, if they were like this, you could say that dividing by 2, this can be transformed to 4/3. They are not like this, rather they are like this, in their simplest fractional form. Okay, so we have p and q here, and let us now make some logical steps and arrive at some contradiction. So let me square both sides. What I get is 2 equals p squared over q squared. If I have this, I can multiply by q squared, and what I get is p squared is 2 times q squared. So it tells you that p squared is twice something, and since this q squared is for sure an integer, it's twice some integer. Therefore, p squared is even. Okay? What I claim here is that it means that not only p squared is even, but it follows that p must be even itself. P is even. Okay? Why? Imagine that p was not even. Imagine that p would be written in the form 2 times some number n plus 1. This is a typical odd number. N is an integer. 2 times integer is an even number, plus 1, it would be an odd number. If you make a square of such a number, you get p squared equals 4n squared plus 4n plus 1, which can be written as 2 times 2n squared plus 2n, and all that plus 1. Since this bracket is an integer, which is then multiplied by 2, this first part is an even number, and when you add 1, you get an odd number. So, if p was odd, then p squared would for sure be odd. but we know that p squared is even. Therefore, p must be even. So p is even for sure. If p is even, then p must be written in a form 2 times k, where k is a positive integer, okay? So it's some number like that. So we can substitute, this form of p into this equation, and what we get is the following: 2k all squared equals 2q squared. We square the bracket, it's 4k squared equals 2q squared, divide by 2 now, and we arrive at the conclusion that q squared is 2 times k squared. Well, what does it tell us? It tells us that q squared is even. Again, using the same logic as before for p squared, q squared is even. But if q squared is even, then it means that q itself is even, okay? The reason for that, if it was not even, then q squared would also be not even, using the proof outlined here. So q must be even also. Therefore, q can be written in a form 2 times L, where L is a positive integer, okay? So here we are. We know that square root of 2 has the form of p over q, as was supposed here. But what happened here is that we have shown here that p is 2k and q is 2l, where l and k are integers. So this is actually the contradiction that we arrived at, and the reason for this being a contradiction is the fact, what did we suppose here about p and q? We suppose that they are in their lowest terms, that they cannot be simplified any further, that this is the simplest fractional form of this fraction. But here we arrived at the conclusion that this is really not the simplest fractional form, that we can cancel number 2 here, and this would be k over L. So this is a contradiction, and since this is a contradiction, then our original supposition that square root of 2 is a fraction, p over q, is not true. It has to be false. So the square root of 2 cannot be written as a fraction. If it could, there would be a contradiction, and in mathematics there are no contradictions. So therefore square root of 2 is irrational. It's not a rational number. Now, a historical side note. The proof of the irrationality of root of 2 is often attributed to Hippasus of Metapontum, a member of the Pythagorean cult. He is said to have been murdered for his discovery, as the Pythagoreans didn't like the idea of irrational numbers. They tried to build their mathematics on rational numbers only, and they were something of a religious cult. So they didn't like people who showed that something else was true as they believed. So therefore, he is said to have been murdered, and this is a very interesting story, a historical side with this.